Remember, you had several extra days. Yours has to be even better than the awesome presentation.
Okay. So, redispatching in an interconnected electricity system with renewables penetration. So, the basic ideas of this paper was that the deployment of renewable energy at areas of the grid with weak connection and far from the load centers could lead to overloading of transmission lines. Redispatching was often needed in these cases to ensure the safe and reliable operation of the grid. In addition, they studied 3 different, variables included in redispatching, which were loop flows, the addition of more renewable generation, and the relaxation of N-1 security criterion to see how that affected the price of redispatching. So this is going to get explained more in depth. So transmission line constraints. Transmission lines have ratings based on the material of the line that determine how much power can safely flow through them. If the line is forced to carry too much power for too long over the rated limit, it can lead to overloading the line, which generally has bad consequences. So, congestion occurs when transmission lines constraints have been violated and congestion management needs to be taken to relieve it. According to the Association of European Transmission System Operators for Electricity, 80% of the bottlenecks identified in the European grid are directly related to renewables integration.
What year is that? Do you know?
No.
Like your paper or?
I think it was pretty recent because it was talking about, the main case study was about adding power in about the 2016 Belgium grid, or what's going to be. So I think it's pretty recent. So in electricity market, transmission constraints are taken into account in a pretty limited manner. Like what we did in class, we considered the transmission constraints between 2 areas. And this is what they do to determine for transmission constraints when trying to determine the economic dispatch just between 2 areas. But the problem comes into effect when within one area there's transmission constraints that are limiting the amount of power that can be used to service the load within the area itself. So redispatching is what they do to address this problem. So after you make the day-ahead schedule with the amount of power generated and the amount to match the amount of demand with the day-ahead schedule, they do that without taking transmission constraints within the area at all. And then afterwards, they go in and say, hey, there's an overload because you can't actually get all this power generated in this area to serve the rest of this area. So now you have to do a redispatch to try to address those concerns. So redispatching has cost associated with it. If you increase conventional generation, you have to pay that generation for the amount of power it's now producing. If you decrease conventional generation, that generation now has to pay you for the power it's no longer producing. In addition, there's cost with curtailing renewable energy, because due to regulations, if a renewable is not producing energy that it could be producing, then you'd have to pay it back for the energy that it could have been producing. And the 2 large prices over here is loss of load, and if you are forced to curtail a renewable resource that has a contract that says you are not allowed to curtail this. So, in the model used for evaluating the redispatch, first was trying to determine the optimal day-ahead scheduling for the bidding zone using a unit commitment model like the one we used in class, where transmission constraints were only taken into account between 2 different zones. Afterwards, it used a DC power flow to evaluate the day-ahead schedule, and then used redispatch actions to avoid transmission line overloading in the bidding zone. And any differences from the day-ahead schedule results in net cost for the TSO, and a creation of the optimal redispatch model was trying to minimize this cost. So there were assumptions made in this model. For one, all generators were assumed to produce a reliable amount of energy. So wind, which is generally goes up and down, was just assumed, okay, it's going to produce this much energy for the case of modeling this. The The time step they used was hourly, and all conventional generation sources were assumed to be capable of being turned on and off and being able to ramp up and down. So the model they used it's fairly similar to the one we used in class. The only difference is that it included these two terms, which this one is the cost of just turning on the generator, I'm pretty sure, and this was the startup cost. And Z and V were just used as like on-off switches on whether it's on or off. And this one was marginal cost times the amount of generation. Marginal cost times the amount of generation needed from each generator.
Marginal cost, or it shows marginal?
Marginal generation costs.
Oh, okay, it's times, so it's in linear costs.
Yeah. So the objective function for the redispatch model was like Zi minus Et. If it was on and then it was off, that would be 1 minus 0, so it's on now. So that's just taking into account the differences in the redispatch from what was in the original. And it added 2 additional terms over here for the cost of curtailing loads and the cost of lost load. So in the Belgium power system, what recently occurred is that by 2016, there would have been 800 megawatts of offshore wind installed. So this has caused redispatching to become an issue within this area, as the transmission grid connection to that 800 megawatts wasn't strong enough to supply all that power. So there was a focus given to the 380 kilovolt system along with the 150 kilovolt system, just to try to focus the area of the study to connecting the offshore wind. Like, there's more transmission in the area, but only these parts of the grid were considered. And to determine how much power is gained from renewables, they just used historical data. So this is just an overview of the grid and I guess typical characteristics of certain types of power for that. And up there is the parts of the grid that they considered.
Belgium's up there somewhere.
Yeah, like this whole thing should be Belgium. Over here where it's highlighted in gray, that would be the area where the overloads were occurring and redispatching was needed. So, in the results of the study, it was shown that redispatching was needed 23% of the time, of the entire time the grid was operating throughout the year. But only 0.8% of the total load annually needed to be redispatched for a cost of about 2.9 million euros per year, and around 34.3 gigawatt hours of upwards or downwards redispatching was needed. By definition, upwards dispatching and downwards dispatching is equal, because in order to serve the same amount of load, if you turn off the load in one part of, if you turn off generation in one part of the grid, you're going to need to turn it on in another. So upwards and downwards should be equal, and that's how much needed to be redispatched. So one of the considerations that they took into account was loop flows, and how doing a loop flow instead of just like, so loop flows are power flows through one part of the grid caused by injections or withdrawals in another. So in the case of the Belgian power studies, power would be coming in and out of France or in and out of the Netherlands. So considering loop flows within the system changed the amount that redispatching was cost. So if you didn't consider loop flows at all, this would be the amount of redispatching needed, while if you did consider loop flows, negative loop flows would cause a pretty decent increase in the amount of redispatching needed, while a positive loop flow would cause an increase, but not as drastically. They also considered what would happen if you decided to install even more wind power into the system. And in that study, it was shown that there was an increase in redispatching needed in that case. Okay, so finally there was N-1 security criterion. So far in this paper, a curative N-1 security criterion was implemented in the redispatch phase. So it's pretty much, if a contingency was going to occur, you were allowed to use redispatching to solve the contingency. In a preventative model, which you can't use redispatching to solve contingencies, costs were dramatically increased. So I guess to explain what N-1 erg security criterion is, it's pretty much, if you have a line that goes down, you need to be able to ensure that power is still being able to be delivered and you're not going to blow up the grid just because you have a line failure. So N-1 security criterion just kind of make sure that in case a part of the grid goes out, you can still operate the grid as a whole. So the N0 criterion is normal operation of the grid where nothing's going out. So you wouldn't really need redispatching there, but for N-1 curative, then that causes that. And for N-1 preventative, there's even more redispatching needed, I guess.
Hold on, before you, this is so, it's hard to understand. So, it's a typical thing. I mean, N-1 means that the unit goes out, you can still run. And it won't break down the grid. And here we're talking about transmission. I don't understand.
For N-1, that would be line. So if a line goes out, then you can still run the grid.
And preventative is no real-time control. It's only, what does that mean? So no dispatching really is contingency. So you know redispatching or?
I think you can't use redispatching to solve contingencies. You can still use it for beforehand, I guess, but you can't.
And so, okay, the definition of N0 isn't clear at all. So,
N0 is pretty much, N-1 is if you take something from a part of the grid, or you take a line essentially and you remove it from the system and you're trying to make sure the system can still run. N0 is pretty much, this is the grid running as it should be without.
So no problem.
Yeah.
It's a baseline of 0.
Exactly.
And there's a smaller loss of load for preventative and curative, and that's because of what?
Actually, well, I think it's just the color scale that's a little bit off.
Oh, there's 2 whites.
Yeah, I think it was a little bit more clear, either on my computer because it's not clear at all.
What are the 2 bars then? So for N-1 curative and preventative, you have 2 bars.
So,
What are they? Why are they 2 bars for each?
So one of them is upwards dispatch and one of them is for downward dispatching. So the 2 bars should be equal because upwards and downwards are about the same.
Oh, cool. Okay. And so what's res minus?
So that would be the cost of taking away renewables.
Taking away renewables. Okay, cool. So it is true. So the second bar is loss of load.
Mm-hmm.
And for the curative case, it's twice as big as the preventative.
That's adding load, that's...
In the second bar,
I think that's subtracting conventional.
Really? Okay. What the loss of load?
There's, because in the paper it was saying that loss of load only occurred in N-1 preventative.
Okay. Oh, that is okay, more. Okay. Strange. All right.
So in conclusions, from the Belgian case studies, these conclusions were drawn that loop flows can have a large impact when redispatching, that the transmission grid constraints limit the amount of renewable energies that can be connected to the grid in a certain area once congestion start to occur. And if you start injecting more renewables within that same area, that the problem just starts to increase more and more. And redispatch costs are about 8 times higher when preventative N-1 security criterion are opposed as opposed to curative. And I guess that's it. Okay.
Questions?
Okay.
Can you explain a little bit more about that N-1 preventive versus curative?
So,
What's the difference?
so pretty much a grid should be designed so that it can operate in the case of an N-1 contingency. So for curative, it's pretty much if a contingency occurs when a line is dropped, you are allowed to use redispatching to fix that problem. For N-1 preventative, you are not allowed to use redispatching to fix the problem. Like, you have to, like, I think that the way I kind of understand it was that after you do the system, after you do the system analysis for the day ahead peak, that then, for the day ahead scheduling, that then goes to the TSO who determines whether or not the schedule is reasonable and then makes redispatch things. So in curative, like past that point, I think the TSO is still allowed to make changes, like if he sees that an overload is occurring in this one place, to turn it off and turn it on in real time. While in preventative, the TSO would just have to make sure that no matter what, in the redispatching orders, it would prevent all N-1s, like without having to redispatch in real time if a problem does occur. So I think that's how it is.
Okay. So it's a couple of points that they make this claim that additional renewables will cause this huge extra problem. And as you said, the assumption that they'll remove conventional generation. So, I mean, that sounds very political. I mean, how would you respond to that in the situation?
Okay, first, I think it was kind of stupid to add renewable generations to an area that wouldn't be able to support it in the first place. So I think that the problem that the Belgian power grid is having could have probably been prevented if proper planning were taken into consideration beforehand. I think it was more, the paper was more trying to address the problems with, or trying to see redispatching costs, or trying to just explore how much of an impact adding renewables had on redispatching. So I think that if it was political,
No, it just sounds like, not that they are, but that's how these things are used. I mean, it's, renewables are costly, forget it. Right? But maybe it was because it's very strange that they said, we're going to get rid of the conventional generation. I mean, if you comment about,
like, I don't think,
about good planning, that sounds like very bad planning to me.
yeah, like
You see
for
why I say that?
like for getting rid of conventional generation, like decreasing conventional generation gets the TSO money, so I guess that would be preferable to them in their redispatching operation than just curtailing the renewables, which would cost them money. So when they're trying to figure out the redispatch orders, like if you can curtail conventional generation, that's probably the first one that's going to go.
Yeah, but, right. But, I mean, part of the reason, don't you agree that they could be causing trouble if they assume they're going to get rid of a lot of conventional generation? That could be a source of the high cost they predict.
Yeah, I mean,
You see why I'm saying that? Or?
are you trying to say that, like, could you elaborate on that?
Well, just what we're talking about, the generators are not just for supplying energy,
Mhm.
supplying
Yeah.
other services.
So I do think that if it costs money for if conventional generations have to pay to not produce essentially, then that does put them at a disadvantage to renewables in that scenario. And I think it's mainly due to regulation that they want to increase renewables. They want incentive to use renewable energy as opposed to gas or oil. So I think that's why they did that.
It's bad planning, so it's bad planning, as you say.
Yeah.
Getting rid of a resource like conventional generation is silly until you have.
Yeah, and I think it does cause a problem that, like, adding these renewables is increasing the problem, and they're the ones to benefit from increasing renewables, which,
Who is?
like, adding the renewable generation to the power grid was the one that caused the redispatch problems in the first place, and adding those redispatch problems because renewables were favored in this situation does seem a little bit. And the thing is, the renewable wind that they added to the system was curtailable. So that means that if you shut it off, they would be paid for not producing.
And why is that? Because that's not true everywhere. That's true in Belgium.
It depends generator to generator. Like, some generators have a contract where it's curtailable generation, where it's like, if it's going to cause a problem, you can decrease it, but it does have a cost. Other generators in the system are non-curtailable, where you're really not allowed to turn it off. It's producing power, it's going into the grid.
They were lucky with the contract years ago.
Yeah, they were lucky with the contract that the offshore wind that they installed was curtailable. So I think that contract did kind of benefit the generators.
It benefits the grid. I mean, controllability is valuable to another degree of freedom. And so, do you have any insight on why loop flows are causing so much trouble? The huge cost that you showed.
Okay, where was that?
I mean, it's
So,
and does that really happen? That you get 2 gigawatt hours? I mean, is it such a big problem? So, yeah, that's a good question. I mean,
so I think that
nobody understands if this is a big deal or not.
So I think it was a big problem with negative. I think that was the case when it was getting more power, when it was already experiencing overload powers. Like, it's going north to south, and the problem area. So I think it's just like injecting more power into an area where there was already overloads, and that needed more redispatch to try to control that.
So they're getting too much power.
Yeah. Like, if you considered Belgium just inside Belgium, then, like, without the loop flows coming from Netherlands and France, then that's one case. But considering loop flows where you can get more power or more power can come out, that causes an additional thing to consider.
But this couldn't happen in North America. Do you know why? I remember ACE has 2 components to it. And there's a frequency deviation. Remember the second part of ACE?
No.
The tie line error.
Okay.
Yeah. What you're talking about is a 2 gigawatt hour error in the tie line. So how can they just let that happen?
Is that within an area maybe? Or not? Maybe it's not.
You were talking about this going from France to Belgium, right?
Yeah, like France and Netherlands into Belgium, and that's the difference.
Float around like that?
I think that this is like if. Okay, so it's pretty much if this amount of power was included.
That's the thing I remember, so that would never be allowed to happen in North America. It's like they set it to 0 every hour or something.
Like, I think they were just considering the possibility of what would happen if this amount of power was injected, if these amount of powers were injected. So it might not be an entirely realistic approach to it, but if you did consider power coming in and out of Belgium, out of France and the Netherlands, this is what the effect that it would have on the redispatch.
Okay. So it sounds like a red herring to me. It sounds
Yeah, I think it might be a bit of a red herring here.
Any other questions? Thank you again.
This is my paper that I selected. I had selected a different paper earlier, but I couldn't handle the algorithms in it, so I switched to a simpler one. It's a really simple paper, and I recommend everybody to read it once, and it's basically a supplementary for what we already studied in this class.
The slideshow? Yes, that's the slideshow.
Oh. So this is the abstract. So the authors use FERC order 888 to define all these ancillary services they have used in this paper. The order basically was a really big thing in power industry when it came out. It basically defined ancillary services. Earlier the ancillary services existed, but they were integrated into the power generation, and they weren't a different entity altogether. But this order had defined each ancillary service as we know them today, and it really opened up the energy market to everyone for competition. It also made ISOs and RTO transactions more transparent, and that's why we get to see all the real-time bidding, auction details and everything on websites.
Do you need energy market or do you need ancillary services market? You've been seeing both
The ancillary services market.
ancillary services, not energy.
Like the ancillary services market was separated from earlier it was like just integrated into the energy market. Like there's no separate market for ancillary services. So why do we need these markets? We need ancillary services basically. So, and in order to make ancillary services more attractive for generators rather than usual active power production, we need markets that support these services and compensate them well. So these are the two.
Slow down if you're having trouble. Just make sure you go away. Okay.
So the two types of markets we have are dynamic and cost-based. So dynamic are the ones which keep changing on real time. The prices for services keep changing according to the load and generation. And these are the usual ones like power generation, that's active power injection, frequency support. On the other hand, we have cost-based, that these are basically set beforehand, and it's not real time, it's not dynamic. It's set before a day ahead market or something. And the example for that is Blackstart. Blackstart is basically a service where a generator can start itself without using any of the grid's energy. So it doesn't, like if there's a complete shutdown, it's a isolated generator and it can start up itself. So there are 6 services that the authors talk about, and these are the scheduling, system control and dispatch. So this is the basic economic dispatch that we have talked about in the course. And then reactive supply and voltage control. This is something still in progress. It's not really a mature market as of now. And for now, it's because of its problems, it's still a cost-based service, and research is being done to convert it into a dynamic market.
Which one, please?
Reactive supply and voltage control. My earlier paper was actually on that, but I couldn't prepare for that properly. And then regulation, frequency response. This is what we have studied a lot in this course. All about Droop and stuff. So frequency response is defined by Droop response of governors immediate response, that is primary control of primary loop control, is not actually a separate ancillary service. It is a it's not given any extra. It's not given any extra compensation for the service. It's integrated into the market. Energy imbalance service. Energy imbalance service usually the service of real-time markets, balancing out the imbalance from, and this hasn't been like talked about much in the paper. And then the reserves, spinning and supplemental reserve.
But you're going too fast, so you cut slides and you've got, it's like, make sure you just make sure what's okay, that's good.
So spinning reserves are like control. The regulations are made by NERC, and they are basically like consistent between day-ahead and real-time markets because it's based on the prediction of load on that particular day, and loads don't usually change as we get closer to. We can't really predict a load better as we get to a real-time market. So they stay consistent. The NERC has a regulation that at least 50. The spinning reserve should cover for the largest possible contingency, and it should be online within 10 minutes. These are the two requirements by NERC for spinning reserves. But the ISOs usually provide 50% of spinning reserves, and which I felt is like a little too much, because 50% of reserves means we are wasting 50% of these generators, which are usually the economic generators, and hence driving up the marginal price. So this is not really, the spinning reserves are not really affected by renewable resources. So
that's a huge statement. So why? The things we're getting, I see what we're getting bombarded with statements about justification. Because there's so many statements here. And a lot of them I'm writing down notes to myself. This is a big one. Who's claiming that? Is Kirby claiming that, or yourself?
yeah, it's in the paper.
Do you know why?
Yeah, because should actually increase, yeah.
That's a huge statement. I mean, think about like the plots I've shown from the Pacific Northwest, right? I mean, there they. Yeah. I mean, so if you don't know, it's okay. But just,
I prepared for it. I kind of forgot right now. I'll get back to you on that.
Just make sure it's clear in the report.
Yeah. So pricing, it's the rated at the shadow price of inequality constant. That is basically the maximum price. Like if the maximum value of of the price is decided to be something, and then that is usually the price that is given to the generators.
And the first thing, do you know what that means? The shadow price of the inequality constant?
So the price is actually like if the price is less than or equal to something, then that's the highest possible price is actually used for paying the generators.
Do you know what that statement means? Do you know what a shadow price is? For an inequality constraint? Like which inequality constraint?
Like less than or equal to something.
No, what? What's less than
If
equal? Like
so, like it's the marginal price. Like if one of the generator has a higher marginal price, so the price should be less than or equal to the price of the highest marginal price of like the costlier generator.
that's not what that statement says. So that's yeah. The shadow in that context, it usually means Lagrange multiplier, but if there's some inequality constraint, say transmission constraint, I mean, that's what the language usually means.
I understood as like the graph we had done in class, like we use the slope of the costliest generator, and that's what I thought it
Well,
meant.
that's not what it means in this context. It's something else. I mean, inequality, usually they're talking about locational marginal prices or something. I mean,
Yeah.
in that case, it's like an inequality constraint. It's like the LeBron.
So I thought it was like some,
Yeah.
like so this was the costliest generator. So this is the price that is the, like it should be less than or equal to this price. So that's what I understood.
Well, I mean,
Like
that might be true. Yeah, that's not related to the first bullet. And the second bullet, are we talking about ancillary services for the second bullet?
yeah.
Okay.
So second bullet actually, 745 was rejected because, this is my point of view, it's like 745 was rejected because it was paying for arbitrary prices. So even in this, like we are deciding arbitrarily that we can pay $10 extra for lost opportunity cost. So when this is justified, then in a way 745 is also justified. So I felt that 745 could have still stayed in this, like when you're paying for this thing, you could have paid for demand response as well as a lost opportunity cost.
Okay, so I guess we'll get to the last before we move on to the next slide. So another case for what? What is
So
the-
it's when load is low, then we have multiple cheap generators.
Okay, so just want to make sure I understand. Another. Oh, this is one scenario. Okay, go on.
So when the load is low, then we have a lot of generators which have low marginal price, and all of them are competing for production. So the overall cost is low. So at that time, there's no opportunity cost for generators providing ancillary services, because if they were providing active power injection, then they would actually be making very less. So there's no opportunity cost in that. So when the load is low, we don't have to pay opportunity cost for ancillary services.
So is this your editorial comment or theirs?
There's
Theirs. And so they feel that there should be less payment for capacity or spinning reserves if the load is low? Or?
So when the load is low, the generators which are already running at a low capacity, because the load is low,
Yeah.
and also they are providing ancillary services, in that case they don't need to be compensated for lost opportunity cost.
Okay, that's the comment.
So this is a curve in which, like for this generator, the marginal cost is $18. So they would prefer to shut down if the marginal price is less than $18. So if that's generator is providing ancillary service, then cost to keep it running is really high. In the two cases, the blue line shows cost in which, in the case when the generator has to be running because it's committed to the ISO, and the black line shows the case in which the generator has the option to shut it down itself, but the ISO requires it to be providing ancillary service. So in that case, the cost is like really high, and as the marginal price increases,
So this is the cost to who? The cost to the balancing authority or?
cost paid to the generator by the ISOs.
Payments to, so the payments, so not the cost, it's payments.
Payments.
Yeah. So why does the payment get so high when the spot price gets low?
Because in this region they prefer to be shut off instead of running the generator. So in order to make them keep running, you have to pay a lot more than the.
Wow. Why? Do you have any insight on why that much? Why would it jump from $10 to $75?
Because the capacity of ancillary service is like really low, but the generator has to like still start itself, so the cost of starting up is high, and to make it more attractive they have to pay a lot.
That's strange. It's just strange that it's monitored. I mean, as the price goes down, even for the dash blue line.
So the dash blue line is in the case when the generators like commit, it has to like keep running. It's because it's like it's contracted to be running.
Right.
So in that case,
Do you have any insight why it would go up though as the stock price goes down? It's really, it's very peculiar.
yeah, because like the marginal cost, like the cost of generating for the generation for the generator is $15 to $18. So since it's less than the spot price is less than that,
Oh, so it's a two payment. So there's the spot payment plus this? Or?
no, it's just one payment. But when it's less than $15, like in order to keep like in order to make them provide ancillary service, they have to pay a little bit more than the spot price.
So then if the spot
So-
price is 10, they get even more, it looks like. It's strange. The lower the spot price, the more money they make. Okay, it's confusing.
So what's the effect of renewable energy on pricing? So increasing the renewable energy means more volatility and hence more reserves, and even so yeah, this part contradicts the earlier part.
Oh yeah.
I realize it right now. I don't know how.
Depends on what you mean by reserves. I mean,
Spinning reserves don't have any effect on.
Well, I don't know if that's true.
Like if there's no volatility, in the system, then it's really easy for ISOs to optimize production and make everyone happy in that case, in such a case. But when there's volatility, it's difficult. It becomes difficult to optimize because there's so many uncertainties that it's really difficult for the ISOs to optimize this, and hence the prices are actually not optimal when they start becoming disrupted because of renewable energies.
Do they use the term optimal prices? Where the prices may not be optimal? Is that their language?
I think so.
Because that would be hard to define. Do you have a definition for an optimal price? Or might be hard to.
It's a price in which not everyone is making money.
Yeah. That's not
So cost allocation of the ancillary service, when the ISOs are paying the generators to provide ancillary services, and the ISOs get this money from the consumers. But what happens if a single consumer is responsible for half of the regulation burden of a certain balancing authority? But when he's paying the bill, it's all that effort is it's being distributed among all the consumers, and he's not paying anything. It's not according to what he's using. But on the other hand, when it's about power usage, then it's going to meter, and how much ever he uses, he pays for that. But it's not the same with ancillary services, and the author suggests that they should design a market in which the consumers have to pay according to the usage of ancillary service. That is being done on the generation side, where renewable resources are being charged extra for introducing volatility in the system, because that increases regulation burden. So potential changes to the existing designs. need to adapt to the market changes in renewable energy generation sector according to
Well, we can't hear you. So what is important? So make sure we can hear you.
So there was a survey in which they were like they predicted that when the amount of renewable energy reaches 30% of the total energy production, in that case you can't have the same model of energy pricing of services as it is right now, because with renewable resources prediction gets better as you get closer to real time. So but on the other hand, it's not the case with loads. So if it's just loads, you can just the cost stays static basically. But on the other hand, when renewable, you can predict better, you can change it like real time on real time. So the authors say that it's better to switch to a market where the cost is not static and it can be manipulated real time basis, which does not happen right now. So this part of the this thing, he talks about battery technology. There's a two-line sentence about battery technology, but following that there's a line, this particular line: the ancillary service requirement is based on the need of that service and not tailored to the conventional market participants that are currently providing the service. This somehow related to FERC 755 because that was brought about by battery manufacturers. And 755 made sure that it's like better performance generators are paid more in that situation, and it's some sort of related to that.
So there's two clauses here.
No, this is not included in the paper.
But they do say that the ancillary service requirement is based on the need of that service.
So this sentence is included in the paper, but FERC 755 is not mentioned.
No, sure, but I'm trying to understand how these two clauses are related. So one is that the ancillary service requirements are based on the need of that service. So that's right. I mean, what
I relate it to in a way that quality does not matter.
What's that?
Like currently the quality does not matter, and the authors wanted to like the quality of generation should be a factor when pricing is decided. So that's somehow related
So
to.
the requirement's not tailored to the conventional market participants. And what does that mean?
It's not ideal for the higher performing. That's what I inferred, like higher performing generators, because they are being paid the same price as the lower performing generators.
But these are ancillary services. Is that what that means? I mean, if it says the ancillary service requires based on the need for that service, and it's not tailored to the conventional market participants that are providing the service. So the service must refer to ancillary services, not energy. Right? I don't know what Kirby's trying to say there. Yeah, so in your report, make sure you understand that. There's some content there, but I don't know what he's saying. I'd love to know what they're really suggesting. I mean, so changes clearly need to be made. Do you know any concrete changes that they propose?
Yeah, they'll be proposing next.
None of those I can't see. What is it that they're proposing? They state the problem for sure.
So the first proposal was that pricing should be dynamic rather than static. Because
So they have more real-time markets.
yeah, so I have actually included that in the report that it's not like I'm against it. That's what
No, I'm not necessarily against it. It's just that seems
because it's so 30% right now we are at 5% of total generation. It's a long time.
Well, no, but it's, you know, that BPA it's better than 30. In parts of the U.S. it's much better.
Okay.
In Texas it's massive. 40. But that was the only. I mean, is there anything else besides
Yeah.
more real-time pricing?
Yeah.
Okay. Well, here we go. Okay, click.
So this is basically the reason why they need new market designs, because volatility is increasing, renewable resources are increasing. So this was a 2012 paper. So load following is a much more important ancillary service right now, especially after FERC 755. So in this he talks about how how following is not a different market, doesn't have a market as of now, but is basically provided by the generators through economic dispatch. And in a case where there's a fluctuation, like you have to follow the load and the ramping rate is too high, then the economical generator might not be the correct generator to be used in that case, because it doesn't have a high enough ramp rate to follow the load. That's why we have to use some other generator with a higher ramping capacity, and that disrupts the order. And he proposes a design for this at the end of the paper. Frequency response, again, so one of the important things that he talked about was recently, I guess because of the regulation changes in the eastern market, new generators have stopped using governors. So that's really like disrupting the primary control part of the group's frequency regulation. And because of these issues, and plus the renewable resources increasing the requirement of regulation, the authors believe that we need a separate market for frequency regulation, which can be called as frequency reserves. And then voltage control is again still a topic under research, and there's a lot of research going on right now. So the main problem with voltage control is that reactive power doesn't travel well in it doesn't travel well in there's a lot of losses during transmissions. So the reactive power has to be injected locally, and the problem with that is that there's no communication infrastructure for the ISOs to communicate with local injection. So it doesn't happen dynamic. It's a cost-based service right now, and the authors want to change that to a dynamic market, and that's happening right now. The research is going on right now to provide infrastructure for that. So this is the new design he proposes, in which it's a combination of economic, there's a modification to economic dispatch, in which according to load predictions and the volatility predictions during the day, different generators can be used. Like if the volatility is high in a particular time period, then a generator with a higher ramping rate should be used, and like that. So that the new system, modifying the current system for economic dispatch.
And so the payment has to do with the
Ramping capability.
what's that?
The ramping capability of the generator. So
So the light blue is more higher payment than the dark blue or something? Strange.
So he says the metric could be megawatt of ramping capacity per hour or per specific time period. paper basically describes the current situation of the ancillary service markets and how they can be improved to provide better markets, better participation. The important thing I noticed was this was a paper after 745, and they never mentioned 745 in this. And some of the paper, like if you read the paper, you will understand that this might be the reason that 755 could have been bought. Like there are a lot of indication that 755 could be coming soon. So that's it. Thank you.
Any other questions? I had some final words, so I don't think I should take time plugging in. What were my final words? I mean, I was, I was going to, send you this. I was going to, should I? Thank you.
Thank you.
Great. Yeah, I was going to. I had some slides. Well, I had some slides actually. Did I ever show you the picture of the moose hanging up in Montana? It's great. You'll see that in power talks sometimes. It's a poor moose hanging on a power line. You know how it got there? Well, it's amazing how they install these power lines. They put up all the posts, and then they get a motor and they spin it full blast, pulling this wire along. And if you're moose walking through Montana, suddenly whack, you're pulled up in the air. It's really sad. So that's one thing left out of the course. I should have showed that earlier. But then there's a list of things that we haven't covered. But these graduate student presentations have been awesome at sort of showing that about the issues of voltage control and both the engineering problems and also the compensation problems that we just saw. And and I was also going to, review, maybe go over some of the stuff on demand response we've talked about already. But I could see Vol internalized that pretty well. And also during the student presentations on Thursday, we saw a lot of these issues come out. That when you do have some sort of local control, you do a lot better than when you don't. So like in buildings, the pre-cooling could be very useful, for trying to do things right, rather than real-time prices. So if the price goes up, you haven't had any preparation, you're in big trouble. You suddenly, turn down the fans, and as soon as the disaster is over, everybody simultaneously cranks up the power again to cool the building. You get a horrible shock to the system. But with some local control of the building, you can pre-cool and smooth everything out. And that was one of the messages at the end and given in presentations. There's a whole list of other things in this area. I mean, all the security issues we've dropped, communication issues, which, this field is way too big for one course. So it's a little bit of a survey, but not big enough. And just a final question, please help me improve the course. So fill out that faculty, they call it a faculty survey now. It used to be called a course survey. But it's a faculty/course survey. And I do read this and take your input to improve the course. So let me know. I guess, for those of you who don't have to run, I'll plug this now. I've got all the midterms here.